That bio sounds like a lot like my mother wrote it. I sent them two. The one I was hoping they would read is this. When I joined Aztec, straight out of school as a mechanical engineer, they suddenly realized I had no practical knowledge or skills. And they put me on the road for a lot of years and sent me all over the world to fix problems with asphalt plants. And so over my 40 years, anything I know that's worth knowing pretty much came from those years. So that's my real background. So in this room right now are those who believe in man-made global warming. Not only believe in it, but believe that anything and everything that can be done should be done to address it. And it's actually a moral issue with those folks. That's one end of the spectrum. There are other folks, undoubtedly in this room right now, who believe just the opposite. They believe it is total BS. They believe it's either at best a myth, at worst a hoax by the political elite on a ignorant public. Those are the two extremes, and there's everything in between. If you're like me, you're influenced by the last YouTube video you watched on the subject. So but I say that to say this. Regardless of the facts, this is a fact also. The changes, there's a lot of changes, and these are some of the drivers in place for all those changes. I'm not going to read all of them, but these changes have the momentum of a freight train coming down our tracks. And our industry, not just will, it is being impacted right now, and it will only ramp up. And so, fortunately, my job is kind of cool in that I don't have to take sides. I don't even have to have an opinion on this subject. All I have to do is provide solutions to you folks that have Aztec plants or have asphalt plants, period. And so we're going to talk about what drives innovation. We're going to talk about what you can do today with your own equipment to lower your carbon footprint. For decades, we've talked about these things, but we talked about them in terms of make more money, be more profitable. Now it's how to lower your carbon footprint, because it's really, a lot of the things are the same. So the plant on the left is kind of where our industry started with asphalt plants. That's a Warren Brothers plant, 1912. If that reminds any of you of the plant you have right now, we need to have a short conversation right after I get through talking. Now, the plant in the middle, or the photograph in the middle, that's pretty much what asphalt plants look like now. And I'm going to attempt to tell you what they're going to look like in the future. My opinion is they're going to look like that, pretty much. You think, well, that's not very exciting. I've got some slides at the end that really show what they'll look like, but the main parts of the plant will look like that. But look at these two pictures. The car on the left is a 1970 Mustang Fastback. The car on the right is also a Mustang, Ford Mustang, but a new one, and they look a lot the same. You can even recognize that the new one is a Ford Mustang. They do the same thing. They get you from point A to point B. But any type of metric of performance, longevity, performance, economy, horsepower, acceleration, anything you want to measure about a car, the new one is better than the old one. Why is that? Technology, the application of technology. I was about to say, underneath the paint, nothing is the same. I doubt the paint is even the same. So, what am I talking about Mustangs? Well, I love Mustangs for one thing. But I say asphalt plants will look a lot like they look now, but the technology that drives these plants and makes them perform, I think will look a lot different in the future. What drives innovation? Well, these are the normal things that make a manufacturer like Aztec change our designs. There's economics, there's mixed design. There's some mixed designs that are a lot harder to transfer heat to, and we had to change a lot of our equipment to make it work. Regulation is one. Now, regulation has touched people in different states. With whether you have to have lime and how you add lime to mixes and things like that. In California, it's touched in a big way, and we're going to talk about that a little bit. But in the future, regulation is going to be a big driver in things that we do when we design our asphalt plants, because you will need solutions for the regulations that will come your way. And of course, competition is always a thing. So these things, economics, mixed design, regulation, competition, they create a need. And we take available technology and we adapt and innovate, and we kind of put the new technology together like a new recipe. Like, here's an example I like to use. Uber. Uber was a disruptive technology to transportation. You'd have to agree with that. What is Uber? It was a combination of 3 existing technologies. It was nothing new. It was a different recipe. GPS technology, software, smartphones. We all carry around powerful computers now. So very smart people put those 3 things together and created a new recipe to get from your hotel to the airport or from the airport to the hotel. Every day, 21 million people choose the new recipe other than the old recipe. So that's how disruptive things can be. So when we talk about the carbon footprint of an asphalt plant, and this is something we're going to see a lot in the future. We have the upstream, getting the materials, the manufacture of the aggregate and getting it to the plant, the transportation, and then we have the plant operation. This part right here, 43% of the carbon produced when you make a ton of asphalt is from the plant. The rest of it is from somewhere else. Well, we're going to talk about the asphalt plant today. Now, if we just look at that bit about the plant, 90% of the emissions or carbon that comes from the asphalt plant comes from the drum, the drying process. And it's important for us to have an idea of these percentages, because when you guys start thinking about, should I spend money on this, should I spend money on this, what should I do? You got to have a foundation of understanding about whether it's really going to move the needle or not. Now let's talk about just some of the facts in our asphalt industry. 1, 94% of the roads are asphalt in the United States of America. To me, that underscores the importance of our industry. No commerce occurs, period, without roads in our country. Hot mix asphalt, even warm mix asphalt. Hey, it requires energy. No surprise there. And recycled asphalt pavement, RAP, is our country's most recycled material. Of course, the average is around 22-23%. So to me, that means opportunity. 2 main reasons, you guys reply to surveys, you say the 2 main reasons limiting you from running more RAP is specification and availability. The specification, the people that write specifications are going to get a lot of pressure to raise those numbers. So the people that have RAP will have opportunities to use more of it. We'll speak about that a little bit later. Hey, here's some good news. Current plant technology, and I'm not talking about Aztec, I'm talking about technology in general. There is technology that can produce mix with 50 to 70% RAP. So we have capability. So our industry is super important. Yeah, it takes energy to make asphalt. We have a huge opportunity with RAP still. And our plant technology can run a lot more RAP than on the average that we're running right now. And There's many things that can be done right now at your facility to make a difference. Low NOx burners have been, ultra low NOx burners have been the standard. You have to have that in order to have a plant in California, and that's been that way for 25 years now. 25 years. And why I say that, we're not in California. That's just an example of how regulation can drive. In a low bid environment, let's face it, you guys aren't going to do anything you don't have to do, because your number one mission in life is to get the bid. So you just can't start buying technology your competition doesn't have to buy. Regulation is the only time that everybody buys the same stuff. In the future, well, for a long time, what fuels do you use? You use the cheapest fuel that you have available. Well, in the future, we will be told which fuel that we're going to, it won't be based on that. That's been the case in California for a long time. You run natural gas, or you run propane and you don't run anything else. Just switching from waste oil to natural gas, just to give you an example, it can reduce the carbon emissions 29%. So as these facts start permeating through our society and people start knowing these things, we'll be mandated which fuels to run. There's a lot of talk, in certain parts of the country about, and the world, about running hydrogen through our burners. It's not hard as a manufacturer. That's not a challenge for us. We've actually run some trials. The challenge is having hydrogen supplied to your plant. If and when that ever occurs, we have the burners that are available to do that. Not a biggie there. Now, I said 90% of the emissions that come from an asphalt plant come from the drying process. And so what's going on there is we have cold, wet aggregate coming into the dryer. We have hot, dry aggregate coming out. Now, what goes on in the middle is important. Part of our heat, the greatest part of our heat from the flame, goes into the aggregate. Part of it goes into the steel. Actually, everything that gets hot at an asphalt plant, besides rocks, all the metal, everything that gets hot is a waste of heat. In a perfect world, only the rocks get hot, but we don't live in that world. So other things get hot. So it's our job to kind of mitigate all the energy lost to that other stuff. So our drum shells get very hot. And they radiate heat away. We can insulate them. We're going to talk about that in a minute. The other part of the heat that leaves the process is the heat that doesn't go into the rocks. It goes out the dryer in the form of hot stack gases. Can we manage that? Yes, we can. We have technology now that we can manage that. So, in fact, that's a cutaway of a Dillman style drum. This is a cutaway of a double barrel. And what I want to illustrate here is, yes, the drum shell gets as hot as any other drum shell, but with some design such as this, the heat is radiated to a place that contains the mix, so the mix has the opportunity to pick up the radiation from the drum shell. So the type of equipment you select does matter. Now there's okay, so how can we control the amount of heat that leaves the drum? In our industry, that's commonly called the stack temperature. Well, that isn't the stack, it's really the temperature of the gases that go out of the drum, but just using the slang of our industry, we'll call it the stack temperature. Usually, we just live with the stack temperature. If it's way too high and our baghouse can't handle it, we do some things to the dryer to bring it down. We'll go through all those things. If it's too low, we do some things inside our dryer to bring it up. The problem comes in when you run both types of mixes, and now what do? Are you crawling the drum every day? And there's technology that makes it where we don't have to do that anymore. We call it the VPAC, but really it's just this. We have a design of flight that will shower pretty well if it's not that full of material, and it showers good if it's really full of material. And then we add to that variable frequency drive technology. We call it VFD, but it's variable frequency drive. So the combination of those flights that work with low or high levels of material in the drum, and being able to slow the drum down slightly or speed it up slightly, enable us to bring the stack temperature down. That's energy that escapes. Bring that stack temperature down or raise it up if we're getting in the danger zone of mudding up our backhouse. So from inside the control house, your operator has control now over how much energy goes into the rock, how much energy exits the drum. In fact, I changed these slides just for this. We call it a stack temperature control, but you really could call it carbon control in today's climate, because that's really what it is. That's what it looks like schematically. We sense the temperature of the gases going to the drum. We've input to the computer what we would like the stack temperature to be. The VFD control changes the rotational velocity of the drum to either speed it up or slow it down to obtain that temperature of the set point. So we can go from, we just have control over that part of our process. Now, here's a number to remember, and I'll give you a memory trick that I use to remember these numbers. Okay, for every 60 degrees, your stack temperature, 60 degrees Fahrenheit, for every 60 degrees Fahrenheit that your stack temperature goes up or goes down, it'll make a change in the production rate of your plant of around 10%. It'll cut your maximum production rate around 10%. That could be bad, could be in the bad direction, could be in the good direction. For every 60 degrees Fahrenheit that the stack temperature changes, there will be around a 4% change in the fuel required to make that 1 ton of mix. It could be more fuel or less fuel, depending on whether the stack temperature is going up 60 degrees or down 60 degrees. Also, the things that we used to have to do when we crawled inside a drum at night, in the dark, in hot drums, there's no way to do that safely. I don't even know another way to say it. So there's that aspect too. And this can also affect the maximum production rate. It can easily take a 250 ton an hour plant to a 300 ton an hour plant, and you can get more tons out that day for the same fixed cost. Now, how do you remember all that? Here's how I remember it. For some reason, 60, 10, 4 are three numbers that are easy for my brain to hang on to. 60 degrees Fahrenheit change in the stack, 10% on the production, and 4% on the fuel. 60, 10, 4. Everybody got that? Okay, this is a photograph of a book that was sitting on my desk. It's the fan engineering book. It's the Bible of fan engineering. And on these 2 pages are formulas, mathematical formulas called the fan laws. And I photographed it and stuck it in here. And so what these fan laws tell us is that when we use VFD technology to speed up a fan or slow down a fan, how does it affect the output, CFM of the fan? How does it affect the static pressure that the fan produces? And how does it affect the power required to run that fan? And this is important to know And what I thought we would spend the rest of our time doing is going through each and every one of these formulas so that you understand each one by the time you leave here. You ready? Yeah. That's often the look I get, and this is how you're feeling right now, so I know that. Here's what you have to know. For a centrifugal fan, let's say your back house exhaust fan, if you use VFD technology to speed it up or slow it down to match your plant production, if you slow the exhaust fan down to 80% of its top end speed, it only requires 50% of the electrical energy to run it at that point. If we slow down a centrifugal fan, for example, the burner fan, if we slow it down 50%, which is like every day at your plant, it only requires 12.5% of the energy. Those are like crazy savings. There's lots of other benefits on those exact drives too from using that technology. But this technology is commonly available from many manufacturers. It's affordable, it's reliable. It's just all new plants just have this, but there's not hundreds, there's thousands of plants in the United States of America that don't have this technology because they didn't come with that technology. So, okay, I've talked about the math of it and what it means for energy. To me, the best way to describe the difference between using speed up or slow down technology on a fan, centrifugal fan, versus an outlet damper, which is basically what we've been using for 100 years. Okay, if you're in your vehicle driving down the road and you kept the accelerator to the floor all the time and you used your brake to modulate the velocity of your vehicle, that would be insane, wouldn't it? But that's like using an outlet damper on a fan. The way you really drive it, you vary the speed of the engine pretty much. We'll forget about the transmission. You vary the speed of the engine. That's like using a VFD to speed up and slow down the motor on your back house exhaust fan. Huge energy savings. So these are things that we can do now on your existing plant. Other places that VFD technology is used on plants, not so often, but we do have very successful customers who do this. They will use a VFD on their drag conveyor, the drag slat conveyor that takes the mix from the drum all the way up to the top of the silos. And what that does, it slows the speed of the chain down to match the production rate, so that basically you don't run the drag any faster than you have to for the production rate. It doesn't really save any energy. It's really done to decrease the wear. And most of our customers who do this, they tell us they have about 40% less wear on their drag. Does that relate to carbon in any way? I think it does. It's not a direct thing that you can measure. It's not like you can tell some regulator, hey, I used to use this much fuel to make a ton of mix, now I use this much. But anything that lasts longer, is a very carbon-friendly thing. So less maintenance equal less carbon. Go electric. Electricity is not the cheapest way to keep things on your plant hot. In most places, it's not. Hot oil is. That's why most of you guys use hot oil. But in the future, this industry will be using electricity everywhere it can be used. When we sell plants in Europe, we don't even talk about hot oil. It's going to be electric in Europe. And in fact, what we're seeing is asphalt contractors who may be in this room right now, who are owned by European corporate entities, are telling their plants right now, switch to electricity. Well, it costs more. We don't care. Switch to electricity. So that's even happening now. I've talked to contractors. We've had that very conversation. So what all can be electric? Well, the AC tanks, of course. The hot oil heat, even the hot oil heater can be electric. Even if we stay with hot oil, the hot oil heater can be heated electrically. The AC piping, the things on the plant that we have to keep hot, like the drag slack conveyor, the silo cone, those are electric now as a standard. The traverse and slack conveyors on top of the silo, all of that can be electric, like now. And the AC tank farm, the AC piping, the pipe flanges, all of that is yes, yes, yes. You don't even think about it. Insulate those things. Even if you're in the category of you don't believe any of this man-made global warming, you want to do that for profitability. There are piles of data on how many BTUs you lose per foot of pipe and on pipe flanges, but it's just do it. Now, what about electrification? Of course, we've listed the components that are available right now. Well, you're thinking, well, he told us that 90% of the carbon produced when you make a ton of asphalt from the plant side comes from the dryer. And we can do things to make the dryer more efficient. And efficient in this context means make more mix with less fuel. We can do these things. So where's the dryer on here? I wish there was one of these cut sheets was about an electric dryer. But on a 400 ton an hour asphalt plant, on your 8-foot double barrels, the size burner on there is 100 million BTUs an hour. So what is that? What does that mean? It's hard to relate to that number because it's hard for our brains to wrap around BTUs per hour. How much is that? But we can convert that number, 100 million BTUs per hour, to units that we're familiar with. Like we're all familiar with horsepower. We basically know that our vehicles have, a couple of hundred, maybe 300 horsepower. Okay, so if we convert 100 million BTUs per hour to horsepower, what do you reckon that number is? Is it 39? Any takers? Nobody wants to raise their hand for 390. Is it 390? 3,900? I saw a movement there, but you're scratching your head, weren't you? It's like an auction. I'm looking for movement here. Actually, if we converted that to horsepower, it would be 39,300 horsepower. That's a crazy number. That just illustrates really the beauty of an aggregate dryer, rotary aggregate dryer, direct heat transfer, burning a inexpensive hydrocarbon with a very inexpensive burner right there. How much energy is transferred in that small space that if we had to do it with electricity, that's the horsepower that it would take to do that. So we aren't there yet, okay? What can be done now? Okay, insulate everything that gets hot? Almost. Almost. Why wouldn't you want to insulate everything that gets hot? So let's look at the drum for an example. I'll ask questions through here, but I'm going to go ahead and give you the answer to almost every question you could be asked about an asphalt plant. The answer is it depends. That's the answer to almost everything. So, here's a couple of photographs of a dryer. The one on the left is a thermal image. Each temperature shows up as a different color. We have a special camera that takes these photographs. Right there, it's 842 degrees Fahrenheit. That sucker is hot. That's radiating. We're wasting heat like crazy right there, aren't we? Looks like we would be. So is it pretty obvious that we should insulate that drum? That's a question. Should we insulate the drum? Well, I just told you the answer to everything. It depends. Okay, thank you. Well, that's 842 degrees, and I don't know if that's even hotter with a different mix or a different firing rate of the burner. It could get hot. I don't know what that drum is made out of. I don't know what the temperature limits are. I do know a couple of things. I know 3 things for sure. If we insulate it, it gets even hotter. We do know that. If we insulate it, we cannot see any signs of heat damage until it's too late. If we insulate it, we can't measure the temperature of it. So, what do you say? You still want to insulate it? It depends. You know, hey, it's an opinion. My personal opinion is, no, I'll take a hit on the inefficiency. It's probably 2-3%. It's not a huge number.
Like what if you tried to insulate it with like some type of liquid?
Heat recovery. That is really the best thing to do to things like this. It costs more. Basically you put a shroud around it and suck heat off and use that hot air as something else. That's the smart way to go about it. You win the prize. This is another example. This one here is not that's not a thermal image. That's just what it looks like at night. And you know, hey, intuitively, it's hard to look at those and not want to insulate them. You know, if we're really trying to make things more efficient. But I'm giving you these little case studies, and I just want you to think about things a little bit differently when you look at them when you leave here. Not everything is just so obvious. Ductwork. Yeah, should we insulate the ductwork? There's a lot of it, a lot of surface area. Heat transfer occurs through surface area. I don't know. I would say not. But here's the thing. Probably in the future, there's a very good chance that the answer will be yes. We do customer schools in Australia. I spent last September in Australia doing customer schools. And after one of the classes, a guy came up to me, one of the Australian contractors. He had a stack of paper like this. In order to bid on certain jobs, government jobs in Australia, he had to fill out all that paperwork. And it was basically a check the box. Have you done this? Have you done this? Have you done this? Have you done this? So in the future, as the regulation picks up steam, if it picks up steam, we may be insulating things at our plants that we never dreamed of, and it doesn't really make sense to, because you want to check the box to bid on a certain job. So that's where we're headed. I didn't come here to cheer y'all up, sorry. Back house, lots of surface area. Probably a good idea. It's probably a good idea. If you live in a cold climate, it's probably a great idea. So I would say bag houses of the future will all be insulated. So what can be done now? Well, a lot of folks have silos that just use them as, they have storage silos, and they're used like surge bins. They're only just used to keep the plant running while trucks aren't there. That's great, and that's what you want to use them for, but you can make a lot more money by using them as a storage system. That's another talk, but using them to keep the plant running efficiently. And the next slide is going to kind of highlight what I'm really talking about there. By keeping that plant running, and what I mean is communicating with your customers who are going to buy a mix tomorrow so that you know ahead of time. You can plan your day. You can start with the finer mixes and transition to the coarser mixes and keep that plant running. No midstreams, no shutdowns. That's the most efficient operation. Will produce the least amount of carbon, for a ton of asphalt. The quality of the mix will be the best because the The highest quality mix you'll ever make is when just everything is happening consistently and continuously all day long at a continuous asphalt plant. And hey, and manage the end of the day stops and starts. We see people shut down with barely a start up and shut down with barely a wheelbarrow of mix, waste mix. We see people fill up one or more trucks when they start up a plant. That is not an efficient operation at all. This next slide comes from a colleague and a friend of mine, and he's very famous in our industry. His name is T.J. Young. He runs the operation for Duval Asphalt in Jacksonville, Florida, and he's been a consultant for forever. And this is one of his slides. And I have no reason to doubt its validity. And I'll read TJ's slide. Plants that start and stop more than 3 times per shift use up to 20 to 35% more fuel. That is an amazing number. And I believe it. And I've showed that number to other contractors, and they say, yeah, I believe it. So there it is. Here's a product that we've never sold in the United States, but it is fairly popular in Europe. And I'll just throw it out there because it's a solution that's one part of the world sees value in it, and it's just to let you know it's out there. And we call it a satellite system. It's specially designed storage silos that are able to unload mix from a truck quickly into those silos. There's no plant, there's no production. This would be located in a city center somewhere. And at low traffic times, trucks during the night would haul mix and fill these silos. And then during high traffic periods, during the day, the mix is used on jobs, inner city jobs. So hey, just to let you know, there's some solutions out there that other parts of the world utilize. That's a little system on the left, and that's a 10 silo system on the right. There's no burner, the permitting is nothing like it would be for an asphalt plant. Our industry, I think, will be allowed and encouraged to run more RAP than we're allowed to use now per specification. It's incumbent upon us to do it the right way. What does the right way mean? The right way is not to make mix that is just as good. It's to use the science of mix design by guys like Brian Prowl over here to make mix that's even better. The NCAT 2009 test track results prove that this can be done. Not just as good, but better. And at what point should one fractionate RAP? I guess that's open for discussion and disagreement, but certainly somewhere around 25% RAP in the future in order to make mix that's not just as good, but make it even better. As an industry, fractionation of a RAP, I think, will have to become a normal thing instead of what we have now. The equipment, the plant equipment has to be there for high RAP. The plant personnel must be trained with best practices and on how to operate that equipment to run high quality, super quality, high RAP mixes. And of course, the mix design has to be there as well. Any comments on that, Brian, since you're here?
No, I mean, and I think 25% is a good one. You know, below 25% is pretty easy, anybody can do it. Above 25% is when you got to start paying attention, but it's very doable.
Thank you. When we look at a pile of RAP, a big ugly pile of RAP, our industry brain should convert it. What we should see instead in our mind is 70 6,000 gallon trailer loads of virgin AC and 28,000 tons of virgin aggregate. That's what you should see when you look at RAP, because that's what it replaces. It's basically worth what it replaces. There are places in the United States who don't have enough RAP, and there are other places that have mountains and mountains and mountains of RAP. They've even named their mountains, Mount Rapula, and names. They have little red lights on top of them so aircraft won't crash into them. For those places who have so much RAP that they'll never use it in all the mixes that they run, there are other products to be made with the RAP. CCPR, Cold Central Plant Recycling, is one of those. That's a whole nother presentation. I'm just throwing out some solutions. It basically uses no energy. It's no heat energy. It's a 97% RAP product. And when you go do a Walmart parking lot, instead of somebody else doing 8 inches of rock base, you do 5 inches of the CCPR. It's an additional product for asphalt contractors to sell. Warm mix asphalt. Everybody talks about it, nobody does it. But as an industry, I don't know if it'll be 5 years or 3 years or 7 years. We are all going to be using a technology, whether it's foam or one of the various vendors who have chemical solutions in the exhibition hall. We will all be not just using that technology, our whole industry will be using that technology to make significantly cooler mix than we make now. I'm almost out of time. Pretend in your mind that you had never made hot mix. You had always made mix at, let's say, 270 degrees. You've never seen mix smoke before. You've never even smelled mix before. Pretend, put yourself in that spot. And I'm a salesman, and I come to you and I say, okay, hey, we're going to make some hot mix. You need to make it a lot hotter. You say, how come? Well, hey, listen to this. It's going to smoke like crazy. Your workers are going to hate it. The neighbors are going to hate you. It's going to cost a lot more to make. What do you say? I'm insane, right? That's where we are as an industry. So you just kind of reverse that and see where we're going to go as an industry. This is June of 2007. Aztec, a local plant, Aztec plant in Chattanooga, made a 50% RAP in warm mix, and this is what it looked like. The silo on the left is conventional hot mix that they made every day for everybody, and that's pretty much what it looked like every day for everybody. And the warm mix is what it looks like on the right. There's less energy. If you work out the thermodynamics and you lower the mix temperature 50 degrees, you just cut your dryer fuel bill by 11%. We actually have contractors who've told us they've measured more. I don't know how. That's the thermodynamics is 11%, but we have people tell us more. I can't explain it. Stockpile management is something Don Brock preached back in the early 70s, and we're still preaching it. Those covers, the aggregate stockpile covers you see on the right, lower right, if you go anywhere in Australia, anywhere in Europe, that's what you will see. You will not find aggregate laying out where rain could hit it. That's just crazy to them. There are places in the United States where this doesn't really matter, but there's a lot of places like east of the Mississippi, certainly where this makes total sense. We can easily manage out 1 to 2% of moisture, which are huge energy savings. So we'll wrap it up here. You know, when we start lowering the carbon footprint in our industry, it's not just going to be you buy this thing and you're done. It's no silver bullet. But here's some scenarios. Look on the left. The A1, that's the materials. That's the transportation. We're going to leave those alone through here. We're just going to talk about A3, the asphalt plant. We're going to start off just burning number 2 fuel. If we just switch to natural gas, we've lowered our carbon output 9%. If we burn natural gas, we pave and slope our stockpile 6%, and only half of the mix that we make is warm mix. The other stuff is as hot as you make it now. We're down 20%. If we do those things and you make all hot mix and you use some blended hydrogen, which actually we is available in some places now. Now we're at 26%. So all along the way, it costs you less to make a ton of asphalt. So taxpayer dollar buys more roads, or how you want to look at it. So far it's mainly good news for us. Plants of the future, what might they look like? They might look like this. We assist contractors in getting plant permits, not out of the goodness of our heart, but so to help them purchase the plant. And it is getting tougher and tougher and tougher every year to get permits for asphalt plants. In Europe, this has been your standard asphalt plant for a long time. This is a plant in France, taken way back in 2013. Those are the cold feed bins. I'll show you what that looks like from inside the building. That's the double barrel that we put inside the building. Those are the cold feed bins inside. This is a plant in Sydney, Australia. That's the plant there. Those are their silos, and that's the drag conveyor going from the plant to the silos. And this is a video I took inside the building. So that's the future. That's been the future a long time ago in a lot of the world, and I think that's coming to the United States. Not all at one time, but location by location. So what might the future look like? Your plants will be barely audible, if all, to your neighbors. There will be no odors or visible hydrocarbons at all. Much more fuel efficient, lower greenhouse gas emissions, mostly electric, covered or partly covered facilities, including stockpiles. What will the future look like? The maintenance will get the plant reliability much greater, plant uptime much greater, continuous monitoring on bearings and reducers. We will all be able to look at you'll be able to look at your plant on your telephone and see real-time energy usage, electrical and hydrocarbons. Operator, basically AI to minimize waste at the plant. Very easy to operate plants. The labor situation ain't going to get any better. So the easier it is to train somebody to operate a plant, not just to operate it, but to operate it well, will be what future plants have as controls. So looking down the road, we're going to see more wrap. We're going to have to really make warm mix. We're going to have almost as many wrap bins as we do virgin bins, cold feed bins, higher recycle. We're going to see alternative fuel. We're going to use fuels we never thought we'd have to use. And we're going to see the application of technology make our old 70 Mustang, like the new Mustangs of today. And we're going to have less impact and better neighbors. And I think the future is great for the asphalt plants of the future. Okay. I'll close out with this. Every morning I receive an email from Richard Jackson of C.R. Jackson. It's titled, "Have a Great Day." And it's just a little tidbit of wisdom to start the day off with, and I'm going to read you today's bit of wisdom. Although, in all fairness, I must say, last night, Stephen Jackson, his son, told me, he said, Dad's not nearly as touchy-feely as it looks like when he sends those things out, so I have to take his word for that. It said, every person you meet knows something you don't. Learn from them. So after this talk, I would love to meet you and learn what you know that I don't know. Tell me something that you know that I didn't have up here on the screen. I would love to meet you and talk about that. Thanks.